large-scale hydrologic processes. And so that's where I want to try and actually land today. So let's start out at a large scale. How big? That big. And what do you see? Lights, right? How did they do that? In fact, this took a year to put together. This was from a special satellite that NASA launched, where they were taking pictures with a regular camera on the satellite of the night sky, and they tried to get it so that there was minimal cloud cover in every location, and over time they were able to stitch this whole thing together so that you actually get to see the full planet distributed at night. And I love it because it's a picture of us, right? There we are, using all sorts of resources to power these lights, creating denser and denser populations, requiring more and more natural resources in order to sustain these large urban centers. And it's quite easy to see that that goes beyond just energy. So put these lights in your eyeballs. You ready? Eyeballs really wide, and we're going to go to groundwater. I promise I didn't do that. I didn't create this in Photoshop. Ready? Lights, groundwater. Lights, groundwater. And you can see that there is a pretty clear correlation. And that's not just simply a statement of, gee, it takes groundwater to make lights. I mean, certainly, it takes groundwater, it takes water resources to generate energy. We know that through the energy production process. It takes energy to generate potable water. It takes energy to maintain these societies. It takes water resources to maintain these societies. And so, if large-scale hydrology isn't your thing, if this is not your day, that's okay. And if you zone out for a little while and look out the window and think about where you're going to go swimming, that's fine too. But what I really wanted to say to you first off, and if there's one thing that I managed to say to you in the next little chunk of time here, thinking on the large scale, it's that I myself, as a student and now as an early career scientist, have oftentimes struggled with the sensation of coming home day after day wondering what I'm actually doing that's useful. Right? I'm not a medical doctor. I'm not out there offering aid to people that need it. It's hard sometimes to put tangible evidence on what we do that is a valuable contribution. And I would say that in all areas of water resource management, that what you're doing now and what you're going to do with your careers in the next few decades matters a lot to the global society, particularly as the population continues to increase. Safe drinking water is going to be a #1 priority. So take heart in what you do at the global scale, even if you work in microfluidics. It's okay. All right, so we're going to stay on a big scale. All right, what kind of big scale? Well, here we were looking at a big scale in space. Let's look for a minute at a big scale in time. How big of a scale? Well, there's a log scale in years. And what we're looking at now are plots or data sets for how fast water and rock are reacting with each other. In this case, we're compiling a whole bunch of different reaction rates for mostly feldspar dissolution, primarily albite. And we're plotting this as a function of how old those rocks are. And so basically what we're seeing here is that there's a very happy, somewhat fictitious world that we all tend to rely upon a lot called the laboratory. And in the laboratory, things react really fast, and the materials that we tend to work with are very young. Meanwhile, as we begin to move out into the real world, we see that as the age of these solids advances, there's a clear correlation with diminishment in rate. So you could have other mineral phases that are maybe forming on top of this solid. You may have heard scary sounding words like armoring or coatings or something like that, right? Some notion that somehow the outer rim of this solid phase that is in contact with the fluid is becoming different than the interior. Just yesterday, I was out outside of town, and there was this beautiful mountain slope, and it was granite, and it had this red look to it, right? And then this truck pulled out in front of us. We were swapping rental cars for reasons that don't matter. And the truck was filled with fresh rock that had come out of a quarry, and it was beautiful gray granite. right? So the material that is interacting with the surface of the Earth and with water is very different than fresh material that you might crush and bring back into the laboratory. This isn't fully understood. And if you try to take into account the fact that surface area of these minerals probably diminishes, that armoring probably takes place, still you can't get the orders of magnitude necessary to resolve this relationship. And it's an open question. It may be somewhat related in part to a similar trend if you can say or establish some kind of correlation between the age of these systems and how long it takes water to get through them. So let's look at another gigantic scale plot. And here again, we're back at the lab where water apparently moves very fast. And in contrast, when we move out into the real world, we see that when we get into these longer and longer so-called fluid residence times, which we've heard quite a lot about already this week and last week, that there's a pretty darn clear correlation in which reaction rates are diminishing. And then it stops again. So if you have longer fluid residence times, you're moving over bigger distances. And maybe that causes some sort of feedback on what you would see as reactivity. And maybe somewhere in that process, this scale dependence shuts down. It's weird, right? So I don't have any huge goals for today other than to study this a little bit. I'm going to spend a bit of time trying to understand this part, and we're going to spend a bit of time trying to understand that part, and we're going to see if we can make a little bit of progress, and that's the goal.
Just to clarify, can you say something about how you measure this?
Yeah, absolutely. Thank you. So most of what you've seen so far is coming from uranium dating for the reactivity combined with alpha recoil. And of course, the travel time distributions for fluid can be measured in a variety of ways that we've already heard about, like, atmospheric tracers. Okay?
Just a question.
Yeah?
So if the fluid takes a longer time to travel, does that mean that that would promote fluid-rock interaction? It stays for a longer period of time in contact with the same phase?
I didn't pay him. That is exactly what we're going to talk about next. Okay, so we're going to start here, and we're going to start thinking about this relationship with travel time. So if we're thinking about an open system, what that necessarily means is that there's some sort of flux in to whatever we're looking at. There's some sort of flux out of whatever we're looking at. And any change in concentration that takes place for a solute inside of that system has to be due to some source or sink term. Okay? That or we're accumulating or destroying or whatever, precipitating, dissolving. And so this gives us some sense of a residence time. A residence time of what? A residence time of fluid inside that system. And you would imagine that that residence time is going to have a big impact on how much of that reaction we see in fluid coming out the other side, right? And so all of that is to say that the change in the concentration of some solute is a result of its transport and its transformation. And that is the secret recipe that we will be thinking through for the next few slides. So what this means when we go out into the real world and start thinking about changes in space is that if you are looking, for example, with distance along some flow path, then the balance between how fast that fluid is moving versus how quickly it's reacting impacts how the rate of change of concentration of that reactant across space, right? So in this case, we have some reaction that's going pretty darn fast, right? Within, where are we? Within 30 meters, we're out of reactant. And if we increase our flow rate by 100-fold, then we haven't run out of that reactant by the time we hit the end of the domain. That makes sense, right? So let's go to a watershed. This is the world's dumbest watershed. It's one hill slope. And above this hill slope, there is one rain cloud. And that one rain cloud rains at a constant rate for all time in one spot. Perfect. I think we have a chance. Okay? So here is the path that all water takes through this hill slope. There's no unsaturated zone, there's no trees, there's no nothing. It's just one flow path. And so you could almost think of taking a beaker in which a reaction is taking place and just moving it along that pathway, and we measure it at the other end. All right? So how much the concentration of some solute changes along that flow path is simply a function of how long it takes to get from here down to here. In other words, the flow rate. And so effectively what we're saying, and this is just the same way of saying something, is that we are assuming all of the fluid that moves through this system is moving at one travel time, right? It either is this travel time or it's not in play. Okay? So, we have a reactive transport model. Lovely. The change in concentration with time is the change over space as we flow and the reaction. And in this case, what I've assumed is that somehow this water enters this system right here with some initial concentration C0, and that reaction proceeds so that C decreases down to here where we measure it. So if fluid goes blasting through this system, then effectively there's no time, and the concentration is near C0. And if the fluid takes forever to get through the system, then there's plenty of time and the concentration is quite low. And we can solve this. We can set up initial conditions arbitrarily and run the thing out to steady state. And this is what you would get out of those numerical simulations. And in fact, you might even feel as though this is a bit of a waste of time, because if you run it out to steady state, then obviously you can solve this pretty easily. Okay? So yes, I realize this is an easy one, but let's just do a little warm-up. So if this thing is at steady state, then we know that the flow rate has to be balanced by this really simple reaction. Okay? I'm going to go fast because it's an easy one. 1 over C dC, and then over here minus K and over Q dx. All right? And usually we pick up a porosity so that that Darcy flux turns into a linear groundwater velocity, whatever. Natural log of concentration equals K phi x over Q plus some constant of integration. What is that thing? Well, we know that at the entry point, in other words, x is 0, C is C0. So what we would wind up with then is the natural log of C over C0 equal to minus K phi x over Q. Or in other words, our concentration as a function of distance is going to be C0 exponent minus K phi x over Q. And the world works. How does the world work? It works like that. Ta-da! Not bad, huh? Numerical simulations sometimes work. Good. Okay, so let's hope that we can find that rain cloud. Many years later, we have yet to find this rain cloud. So if you're still going to assume that things are steady state, if you're still going to average over ranges of time in which we could have some mean precipitation rate, you've got to at least give me the fact that that rain cloud isn't in one spot, right? That rain is falling all over this hill slope, which means that some of the water gets into the subsurface and shows up right away, and it's going to have a high concentration. And some of the water gets into the subsurface and takes forever, and it's going to have a low concentration. And whatever we measure as a fluid packet down here is some sort of conglomerate, average mixture of all of those different travel times. And as we learned about last week, these travel times tend to have characteristic shapes for watersheds. In general, these travel times tend to favor young water. In other words, they tend to favor the stuff that fell near the measurement point. Newsflash. They also tend to have giant tails, or in other words, they tend to have a little bit of quite old water in them as well. And so what are we supposed to do with this? Well, what we wind up with is some characteristic functional forms that describe this kind of distribution in fluid ages of the packet of water that's showing up here. Are we okay? I'm getting some faces. Make sense? All right. It's not supposed to be scary. So what are we going to do about that? Well, we heard about these travel time distributions last time, and it would be really nice to make some use out of them, particularly given that for watersheds, they tend to be fairly characteristic. Yes, there's differences, but in general, they tend to behave more or less somewhat the same. So let me point out a couple of things to you. Can I have those lights again for a minute? This guy is really interesting, right? If we look at the units, none on porosity, units on distance, probably distance, units on flow, length per time. So this part here, this, can you guys see this? This phi x q thing is some sort of a time scale, right? It's the time scale over which the fluid moved through the system. And similarly, k, this rate constant is 1 over time. And so 1 over k must be another time scale, some sort of reactive time scale, right? So it's equally valid that we could think of this thing, you could rewrite this thing as C naught exponent minus T fluid travel over T reaction, which was a very cute way of saying this thing is dimensionless and we know its name. It's a Domkohler number. We've seen them haunting us for over a week now. There's one. All right? So here we have this notion of a balance between these two characteristic time scales, and now we have some notion of how one of them is behaving in the system. So it's as simple as starting to think about convolving one of these functions with that behavior. Can I laser board this? Yeah. All right. So what we wind up with now is rather than wanting a concentration as a function of distance, we want some notion of a mean concentration or a mixed concentration of the fluid showing up at that location subject to all of these different pathways. All right? I tend to get a little loose with notation, so just let's try. And if it's scary, then come talk to me later because it's probably that I used 2 different symbols somewhere. But, okay, let's say that we want this thing to be a function of the mean travel time. Then in this case, what we're thinking about is integrating from time 0 to time infinite. And who's my guy over here? I have a C naught exponent minus fluid travel over reaction time. And let's grab the exponential. I have this mean travel time, this big capital T, or sometimes people say tau, for all I know it's in my slides, exponent, and then it's going to be minus this fluid travel over the mean, integrated for that fluid travel. That's an F. Okay? It's not that bad. So the first thing we can do is we can pull out a couple of things. And what we are left with is an integral. And I can go ahead and pull the minus TF. And we wind up with 1 over T reaction plus 1 over the mean travel time d T fluid. All right, not too bad. Then what? So we're going to integrate this thing. So we're going to wind up with a minus sign popping out. We're going to have a C naught over, and this is going to be our mean, and then 1 over TR plus 1 over the mean. And then we got to evaluate this monster. T mean, 0 to infinity. At infinity, everybody blows up. At 0, this thing goes to 1, and we get a negative sign out. Huh?
Therefore, get a negative sign when the final value is 1.
No, I think we're good. Did I miss one? So then what happens is, if we go to 0, so at infinity, everything goes away. At 0, it's going to be minus that, so we drop this negative. Maybe that's what you were seeing. And we wind up with C naught T 1 over reaction time plus 1 over mean travel time. Or you could think about that as C naught mean travel over reaction time plus 1. Are we okay? Did I drop one? I don't think I dropped one. There, now it's pretty. Okay, that is familiar, right? This is now our mean travel time over our reaction time, which is an awful lot like this guy, our mean flow rate for a given distance over our reaction time. In other words, our Domkohler number came back. If you love it, set it free. And if it comes back, it's yours. And now we have this Domkohler number, right? C naught. And so this thing is going to be phi k x over q plus 1. And what we have wound up with is a new solution to this thing that's got this guy living inside of him. You want to see the solution for the gamma? You can't. You can't solve it. You have to do it numerically. But the exponential is a particular favorite because you can get to this closed form analytical solution. And what happens? Why did we have to go take differential equations? Well, basically what's happening here is we're taking this solution, right, and we're convolving it with something. It could be anything. It could be any travel time distribution you can imagine. But most of them look like this or something like that. And so we're using these guys. And when we do that, out comes our solution. I think I got it right. And here are a couple of other solutions with the gamma embedded in them. I did those numerically. And these are just different choices of parameter alpha. And something very important happens. Behold, that for the same mean travel time, if you were in a perfect world with one tiny rain cloud that rained all the time, you would see this much reaction. But in the real world, where you're mixing fluids together of different ages, if you're using functions that behave a lot like watersheds typically do, then what you see is a reaction that looks less reacted. As if the reaction progress were diminished relative to the uniform flow rate. Okay? It's not that the reaction was diminished. I didn't have to say the word armoring or somehow invoke some sort of process that has reduced this reactivity. It's just that you're averaging over these different ages and you're weighting towards younger, less reacted fluid. And that's the whole name of the game. Okay. What's next? Good. I would like to convince you that this matters. So if you will give me 10 seconds, okay, 10 minutes, okay, somewhere in between, then I will show you one example. This is a map of chromium. Just for those of you who don't tend to think in terms of contaminant hydrology, bad, right? So here was an original source of hexavalent chromium. We heard about this previously. Remember, somebody had a slide with the Aaron Brockovich Mutangi. You had the Aaron Brockovich slide. This is the stuff. It's not the same site, but it's the same stuff. It's a carcinogen. It's very bad for you. And this is a shallow aquifer. Those are streets. And in between those streets are houses. And this is Berkeley, California. I mean, if they knew. All right, so what happened was there was a spill. They cleaned it up. But of course, that doesn't end the story. And what you're seeing here is that that plume has moved that way ever since the source went away. And so here is the area of highest contamination, and then it gets lower as you spread out, and it's flowing in that direction. So you can see how it's gotten smeared out over time. Some people did a really nice study here, and when I say really nice, I mean that they did their due diligence and they took samples from this system and they brought them back to the lab and they actually ran the laboratory study for this reaction that's cleaning up this chromium in situ. And the reason that that's so important is that it gave us a rate constant for the reaction. So there's the concentration changing through time. It also gave us a fractionation for the isotope shift associated with that reaction. And as Jerome so clearly demonstrated this morning, these isotope ratios are incredibly sensitive and super helpful for inferring of all of the processes that are contributing to the change in concentration in this system, how much of this is associated with that change due to the reaction. Yes?
But you said that in the lab, the reaction rates are way different than in the field.
Aha, aha. So I said that, and then I did a convolution integral that said if I knew my reaction rate from the lab and I used that travel time distribution, I think I could tell you what's going on. And that's, you can see the future. Okay, all right. So they went back out into the field and they collected samples for concentration and isotope ratio, and they said, all right, in the lab, here's what we saw. We saw this change in concentration, we saw this shift in the isotope ratios, and this is the constant of proportionality. In the field, they said, ugh, if exactly the same thing were happening, we should be on this line, but we're over here. And no matter what hydrologic model they ran, they couldn't do it with just dilution. They couldn't get that much of an offset. And so they said, we think we're preferentially sampling fast flow paths. We think we're not seeing a uniform system, but we don't know. Conclusions and future work, and off it went to publication. And so we were able to come back a few years later, take the rate constant from the laboratory studies and put it into these new models. And so here what you see is changing concentration, which in this case, and it tends to be the case in a lot of these systems, really doesn't have a lot of information in it. But the change in the isotope ratios do. And here is the same notion of a convolution integral applied to the isotope ratios rather than just the bulk concentration, which again is kind of a dull tool to use in these systems. And what we were able to come out with is a new version of this relationship. So here you see the log change in concentration and the isotope ratio. Here you see the log change in concentration and the isotope ratio. This is what you should see in the lab. Red line is exactly the same as this line. And here are our new solutions integrating those travel time distributions. And in fact, I will go so far out on a limb as to say that this one was in the centroid of the plume, and these two were on the fringes where you would expect different amounts of mixing. So I think, I mean, we just published this less than a year ago, but I think that this is a really powerful new technique. And I'm not saying that travel times are new. I'm saying that isotopes integrated with travel times is something that we're just really starting to understand. And that these isotope ratios of these contaminants, the isotope ratios of weathering signatures, are incredibly sensitive to these travel time distributions. And I think that this is a really cool new direction that we're headed in. I think it's so much that I have to show you that if you had this regular distillation model for changing concentration and change in isotope ratio, the so-called Rayleigh model that's been around since 1902, which is the red line, then I can give you a new Rayleigh model that has an exponential travel time embedded in it, and it looks like that. So if you give me the lab number, I'll give you the field. All right.
So had this been an instantaneous spill, there'd be no travel
you're saying that the travel time distribution arose from the duration of the spill?
Yes, so I'm saying that we are integrating over a heterogeneous aquifer when we pump water out of those monitoring wells, and that we are preferentially sampling towards fluid that got there quickly from the centroid of the plume. So if the spill had just happened,
Or happened 10 years ago or 100 years ago, it would be one travel time. All the water would have been there 100 years.
if it hadn't moved,
But you put the stuff in,
yeah,
start reacting, and everything's been there 100 years. But only due to the duration of the spill, then you get a distribution of travel times. Because otherwise, anything that got to that point.
oh, yes, correct, yes. So, sorry, I should have, thank you, you're absolutely right. This was a tanning factory for leather that was in operation for a few decades. Yeah, icky. All right, where are we? Yes.
So how can it be used as a predictive model, say, for the next 5 years where the plume will be?
What I would say is that we use these kind of models rather than a location of the plume, the component of change in concentration of the plume that was associated with this fractionating reaction.
Right, but there will be other elements involved in that prediction, not just this explanatory model for what happens when you mix over a longer time. Because it's more of an explanatory model rather than a predictive.
Sure, and so if you wanted to run this in advance forward, then you could use a numerical model like Crunch or something like that, which can do all of that. Sure, and we've done it, and it works. Okay, where are we? Here we are, we're back. Okay, so we said that we were going to spend some time trying to understand this thing, and we started off here, and what I would submit to you is that at least to some extent, I think first order extent, this drop of many orders of magnitude and the observed reaction rate relative to laboratory values as a function of how long it takes fluid to get through the system is at least to some extent a reflection of transport control. Meaning that if you're moving out to longer and longer and longer times of fluid mean residence time in the system, you're integrating over a bigger and bigger and bigger range in fluid travel times. And so you are shifting further and further and further away from what you would infer as a lab rate, and you're shifting in such a direction that the larger breadth of travel times you're integrating over, the more diminished that reactivity looks relative to the lab. It's not that the lab rate is wrong, it's not that this rate is different, it's just that you're integrating over different ranges of fluid time. Yeah? I didn't pay her. What do you think is going on here? Say the word again. Equilibrium. Okay, wonderful. So I had one more slide in here before I jump to that, and that was just to say that it may be troubling you that in the real world, when you're talking about rock, that you could possibly be in situations where fluid travel time is actually influencing reactivity. And this is just sort of an interesting thought piece in which they took crystals of the same size, plunked them into the same water, and measured, effectively estimated, because obviously nobody waited that long, how long it would take for those minerals to completely dissolve. And in fact, you see that quite a few minerals that we would be interested in and which we would use these sort of techniques to infer weathering rates for react over quite short time scales, sufficient to allow this spread in fluid travel times to play a role. Okay, jumping ahead. What is that? So let's start thinking about this notion of equilibrium, which is kind of a funny thing to think about in the context of the real world and real catchments. But I really appreciated several of the talks that we've seen so far that took care in explaining different reactive pathways. For example, Philippe did a really nice job of explaining Monod kinetics yesterday morning. And I thought that maybe one place where we hadn't quite checked in yet was in these types of near equilibrium fluid rock reactions. And so I just want to take a moment to be sure that we're all on the same page about how this sort of thing at least is conceptualized in most of the models that we work with. And so it really comes down to one idea. And that is that you can think of the addition of new material from the aqueous phase to the solid phase as occurring, I'm on the wrong side of the slide, as occurring through an irreversible reaction that is a function of how concentrated that thing is in the fluid. It knows nothing about any other back reaction or anything like that. It's just going that way and it's making new mineral. Tell it nothing. Meanwhile, there's another reaction that's taking place at the same time that's causing material from the solid surface to solubilize into the fluid. And yeah, that does not sound like equilibrium, but in fact, that's what we mean when we say equilibrium. What we really mean is that out here in monster person land, where we can't see these individual interactions, what we're actually observing is an imbalance between them. Okay? So if you see precipitation of a mineral, in other words, your fluid concentration is changing with time, then what you're really saying is this way is outcompeting that way. Okay? And if you're seeing dissolution of a mineral, which occurs on this side of the slide, then all you're saying is that this way is winning. Okay? So if you take that sort of broad brushstroke idea of it, then really what we're saying is that it all comes down to a balance between these two irreversible pathways. So if we start to think about that balance, then in this way of thinking, this sort of dynamic exchange, the equilibrium constant is really reflecting the ratio of those two irreversible constants. What are they? That is a really hard question. Again, the isotope geochemists are trying hard to answer that, using characteristic shifts associated with either of them, but the bottom line is you basically can't discern it. What you can measure is this, and what you can measure is this, the overall rate, which is the imbalance between them. So this notion of equilibrium then is reflected as this constant of proportionality that gives us some idea of how these two pathways are balanced. And then really simply writing down a rate law that's operating near equilibrium is just a matter of algebra. I'm not even going to bother you to get up and put on a light. So all we're going to do is just say that there's this forward addition of material to the mineral minus this backward removal of material from the mineral. We can sub in this sort of information, and what we wind up with is this idea that there's an equilibrium constant, there's this sort of kinetic rate, and there's the concentration in solution. And all I did now, don't lose me, all I did was pull the Kp out. See it? That's a new constant, which we refer to as the rate constant. See, those are two constants. We multiply them together, we get another constant. It's magic. 1 minus, and then here is the concentration in solution, which people often refer to as Q, or the ion activity product. And here is the equilibrium constant. So all we are saying when we write down these fluid rock interactions and try to model them with this so-called transition state theory, or TST rate law, is that we are looking at an overall reaction which reflects a reversible departure from equilibrium. How'd we do? It's not mysterious. It is so unmysterious that it becomes mysterious. Don't let it trouble you. It's very straightforward. If you wanted to, you don't have to use this kind of rate law. You could write down two rate laws that fight with each other, and out of it would fall a balance that you would call equilibrium. You could totally do it that way. You wouldn't have a very good way of constraining these rate constants because you can't tease them apart, but you could do it that way. But instead, what we wind up doing is writing down these kind of rate laws that have this bulk kinetic rate constant and this departure from what we've defined as equilibrium. Okay, so here's what this tends to look like if you're using a reactive transport model, or if you've gone into the literature and started looking at some of these weathering reactions, is just that the overall rate, here's our bulk kinetic rate constant, here's our departure from equilibrium, and here's some notion of the mineral surface area. All right, so what does this mean to us in the world? Well, Previously, we looked at this slide, and we understood that if we have a relatively fast, irreversible reaction, versus if we have the same reaction in a faster flow field, we shift up and down in terms of where we see that change in concentration with respect to distance. And what this notion of reversibility or equilibrium does is it basically makes a cap, or a point at which that reaction shuts down. And this becomes kind of a funny thing to work with in your lives, right? Because suddenly, something that is actually reversible, something that is subject to this sort of thermodynamic limit, might not look like it if you're flowing fast, right? You could totally reasonably model this with an irreversible rate law. But if you went further out here and made the same measurement, you might get a little confused, right? So it turns out that the overall behavior of the reaction has this transport component and this thermodynamic limit, this reaction limitation component. And so now what we see is from this sort of irreversible looking world, as we slow down our flow rate, we begin to level out at these concentrations that are not zero. Okay? It happens for precipitation. So here is me running another one of my little numerical simulations, where in this case at the inlet I have a high concentration and I'm precipitating amorphous silica with distance along the flow path. It happens for dissolution. So here's Kate Maher doing a model of concentration of silicon as we dissolve it from 0 up to some equilibrium value in solution. They work both ways. And quite oftentimes you will see Q over K minus 1, and quite oftentimes you will see 1 minus Q over K, and that's because we just can't make up our minds about how to define the equilibrium constant and which one, forward or backward, is precipitation or dissolution. Don't let it bother you. It's just different ways of writing exactly the same behavior. Okay, so we're getting there. How much time do I have?
5 minutes?
Ugh. Well, I was going to do one more little integral for you, but it's not that bad. The point is just that you're going to take this solution that we already did, and you're going to put that other value in there, right? That other rate law. So rather than this, you would have 1 minus C over C eq. And you can just roll with it. And it's really not so bad. You wind up with over here, you have 1 over 1 C over C eq, and that's fine. You can bring the C eq out, and then it becomes, what, C eq minus C. If that's U, then du is minus 1, so you get a negative sign out here, natural log of C eq minus C. You evaluate the constant, and you get that, which is a solution that probably you've seen around if you've gone into the weathering literature at all. And basically it works because remember there's a length scale in the numerator of this Domkohler number, and so if the length scale is 0, then this whole thing goes away and you're at C naught. And if the length scale is infinite, then this whole thing explodes and you're at C eq. Okay? Furthermore, we can now say that this tailing effect is likely associated with saturation control. So there is a point at which you view more and more diminished rate laws as you go out into the real world and mix fluid flow paths together and preferentially sample towards younger fluid. And there is another part of the world in which you've gone to such long length scales that effectively no action is happening anymore. And to put it all together, you can do the same convolution process with different travel time distributions for these TST type rate laws, and here are a few of them that Kate did for this particular example. And again, what you see is that relative to the laboratory case in red, where everything is reacting at the same rate over the same fluid travel time, now if you drop down to an exponential travel time distribution, you would appear to see diminished reactivity. And it works for the isotopes. So for example, using this simulation, I have several different cases of fractionating reaction for these isotopes. And you can do the same sort of analytical solution and recover reasonably well this behavior. There's a couple of simplifications built into this one, so it's not quite so perfect, but I can live with that. And so finally, just to wrap up, what we're saying in sort of pushing the boundaries of applying stable isotope fractionation to understand these weathering systems is that for these broad ranges in mean travel time, those are supposed to be log units, of changing concentration, we have associated kinetic shifts in the isotopes, we have associated equilibrium shifts in the isotopes, and they have unique behavior that gives us diagnostic signatures about these travel time distributions in weathering environments. And Kate said this to me once, and I appreciated it. So thank you. So in the analytical solutions, I don't treat it explicitly, so I consider it a constant. It's wrapped into the rate constant in those solutions. In the numerical model, you can track surface area change as a function of mineral growth. For the numerical models that I showed you, there was minimal change in the volume of the precipitated phase, and so the surface area was effectively constant.
Okay, so constant surface area.
You can make it non-constant, but in these simulations, it was constant. Yeah. Yeah.
So you assume the steady state approximation you predict when deriving, but there could be a possibility at earlier times when it's evolving with time as well, right? So how is that?
That's a great question. If I understood correctly, she's asking what happens if the travel time distribution itself is changing in time. So these transient travel time distributions are really exciting, and people are working on them right now. I'm a little bit afraid to try this, but I'm going to do it anyway. Let me see if I can find, okay. This is a friend of mine who just sent me this. Where is it? Yeah. So what he does is he reads in a real time series of precipitation and outputs a discharge, like for a river, and then he convolves that with that reaction rate law that I showed you previously, but through time as that discharge changes, and sums that up, and he gets a change in concentration in Jerome. He gets hysteresis in silicon concentrations out of these behavior as a function of discharge that integrates the prior to and afterward event. It's the coolest stuff that I think is happening right now. So your question is spot on, and nobody knows. We're working on it right now. This is what is driving a lot of this seasonal solute chemistry dynamics and behavior that we're measuring in rivers and that we want to use to better understand the physics and structure of these watersheds. It's really exciting. Yeah. Oh, sorry. I'm sorry.
I think Keanu had a question, and then John.
Nice presentation, Jennifer. I mean, I have a comment related with the first one about the surfacing, or the specific phasing contact between the chemicals and the rock.
Yeah, yeah.
So the fact that you get in the lab always larger reaction rate values is because most of them are determined from batch experiments, right? And
So those are all normalized to surface area.
okay. Okay. Perfect.
John?
Go ahead. Going back to your rate versus log age.
Yeah.
You say that, hey, it's all about the travel time distribution.
First order, not all about.
Well, but-
Don't pin me.
The confusing thing for me is that you say, okay, so the lab had a certain age, but then there was this travel time distribution, which is, and so we're misattributing the age, really. You're saying that we attribute this age, but actually it's a blend.
It's a blend, exactly,
And
yeah.
is it really that we, but if that were just that the travel time were misattributed, then why would we still don't explain the overall, is it overall just a first order rate of decay that would have so the rate is a function of concentration? I don't quite see the source of the overarching age versus rate.
So if you were to take a packet of water and try to somehow get an age on it, how long it's been down there, what would you do? You might try 018, right? You might try some kind of a cosmogenic.
So
you might run a tracer. And you're going to come out with a mean that represents some, is related in some way to that age distribution, right? And that mean for the travel time of water through the system is not the same as the mixture of reaction progresses that you would see in that same sample. You tend to, when you use these travel time distributions, get skewed towards the younger water. Does that help?
Yeah, I think so. And yeah, I think I got it.
Go ahead.
There was a question when you asked a question about what is causing this decrease to the audience. Somebody said concentration, but then you in your presentation you emphasize that it's really the travel time causing this decay. So I was wondering if there is not something here thinking about concentration too.
Yeah. So I tried to skirt it because I meant to come back to it, so I appreciate your comment. And I think that the concentration part of the story comes in when we fold in this approach to equilibrium.
Yeah, exactly.
Right? So when you get close to the concentrations at which these reactions start to shut down, then by all means, right, the rates are going to slow down. And that's part of the explanation for that leveling off. But before you get there, when you're still in far away from equilibrium land, you can create these apparent diminished rates. And I argue that that's largely a function of these travel times.
But you could also decrease concentration by mixing, for instance, by dilution. So then you would approach the equilibrium.
That's fair, and I certainly.
And reduce your rates.
Yes, and in the very simplistic hill slope models that I showed you, I didn't have any dilution in there, right? So they all had to spend some time in the system, and then you just aggregated, which is why I think it's fun to go and look at real examples like that chromium spill, where even when you take into account dilution, you can still invoke these travel time distributions and get meaning out of them. So you're right. I think it depends on the system that you're working in. But I think that dilution is not an alternative answer, if that's fair.
Can you explain why the travel times tend to be biased towards short travel time?
Oof.
Can you imagine a system that wouldn't be?
Yeah, actually, it drives me nuts because anytime you build a column experiment, you actually bias the other way. It's really annoying. So it's hard to create a laboratory version of this. But the way I tend to think of it is just the plumbing of a catchment, so that most of the water that you measure following an event like this, like here it goes, right? And that's mostly water that fell right there or very close to there. And it's only much later that you begin to recover the water that took a while to get to that location. So I tend to think of, particularly in these event-based systems, that when you get to these higher discharge rates, you're sampling things that just happen to land there and closer to there, closer to the point of sampling along the stream.
So you say your lower axis is just a misattribution of age, because you labeled it as age, but there's a, whoops, it's not, we just got the age wrong. Is that more or less it?
Well, I guess I would turn that around and say, how do you get the age right? It's some kind of a mean. What are you going to plot against?
So whether the geometric or the arithmetic mean, you kind of say we calculated with the wrong term.
I don't want to say wrong. I mean, we have techniques that constrain some number that is a representative of how long fluid takes to get through these systems. It's just that when you then turn to the reactive solutes that are a part of these systems, they are influenced by more than just that one value. They're influenced by the variance. They're influenced by, there's many modalities in that. It's just the consequence of trying to make an XY plot.
Jane,
Yeah.
Is it that you're taking a flex-weighted average of a non-linear measure? So there's no way that you can uncover that average.
Yeah, that's fair, right? Like if you went into the absolute iota of where the reactant starts to go to zero, it actually like goes off into infinity, right? And so it's not a very good problem, the way that it's set up mathematically.
Okay, one more question.
You mentioned exponential distribution for residence time.
oof. Oh my gosh, you need Jim Kirchner for that one. I mean, they tend to use power law relationships. And what you're seeing, so this one isn't based on any assumption. They just read in rain events and got discharge out of it, and you can see something that looks like a power law, right? So it tends to look like power laws, and in general, you tend to go to these, so I showed you exponential and then 2 cases of gamma where that alpha term was increasing. And as you get into larger and larger basins, I'm saying this in a very general term, that you tend to get to those higher and higher powers in the gamma distribution and everything kind of smears out.